So if we think about our microscopic model for a minute, what's happening in our microscopic model of current and resistance and all this stuff? So let's look at it one more time. Let's see. Big wire here. Everything's fine. Everything's fine so far. Something's going to go wrong, by the way. That's what I'm leading up to. Something is going to go wrong. Terribly wrong. We put a battery on it. No problem so far. I'm happy. Everything's fine, fine, fine. Wonderful. I'm having a great day here. So we put a delta V on it, and we get an E field applied equals delta V over L. I have no problem with that. This has a length L. I can accept that. And we said that the charge carriers, let's get real for a minute and make them negative. We'll let them go that way. E is this way. Negative charge carriers are going to go that way. Of course they're going to go that way, right? The E field is that way. Negative charges are going to go that way. And they're going to fall into the battery, complete the circuit, do chemistry. All that makes me completely happy, okay? So everything is fine. So maybe some of you have noticed what's wrong. There's something wrong, okay? The way we set this whole thing up is we said the electrons are going to move with some constant V drift. Now why would it be constant? That doesn't make any sense. I mean, we have a charge here, it's sitting here, we have an electric field, it's going to feel, this isn't V drift, it's going to feel a force. It's going to feel a force by Coulomb's law. And it's got a mass and it's sitting there, it's going to accelerate like that. And this one's going to start from rest and it's going to get faster and faster like that. It's not going to drift. Where did drift come from? So that's the question. Why did we assign a random or a constant uniform V drift when really they should accelerate? Why is current uniform and constant when it should be always increasing when you apply electric field? So that's a problem. It's been figured out, by the way. This isn't like a fundamental problem and, you know, I got to go call CNN and everything. This is known. What we need is an even better microscopic model for current flow in a conductor. And that model is called the Drude model. It's pronounced Drude. I'm not sure why. I'm sure it's related to where he was from. I'm sure someone will correct me in the forums. The Drude model explains why the electrons drift, and it also explains other things. So let's look at the Drude model. Let's see, as a sequence of events, what's going to happen to some poor little electron. And let's look at its instantaneous, its real velocity. Not some average velocity, not some drift velocity. Let's just have the electron sitting there. So let's look at this one. It's just sitting there. Its velocity at time 0 is 0. Right? You apply a voltage. You apply electric field. It feels a force this way. And it does indeed accelerate. Okay? And if it accelerates, that means its velocity increases in time. So it doesn't move at V drift. Its velocity just speeds up, and it goes faster and faster and faster and faster and faster. That's what really happens until it collides with the lattice. Oh no, right here, it collides with the lattice. The lattice meaning all the crystalline network of all the atoms that are making up the metal, in this case, if it's a metal. Okay? So it can move along, and you could think of it, it's not really like this, but you could think, you know, if you have a lattice that's nice and uniform, and if you imagine some electron just sitting here accelerating, you know, it can miss and miss, eventually it's going to hit. It's kind of like that idea. You can't get through there forever without hitting something. And now, what's going to happen when it hits the lattice? Well, it's going to bounce off, and if we're doing freshman physics, there's going to be some conservation of energy and momentum, and you can think of it as a billiard ball. It'd be a big mess to think about that. So here's the model. Remember, physics is never, you always use a model. The model in physics is that it just stops. The Drude model says, don't worry about the actual collision and which way it goes and keeping track of all these electrons. That's hopeless. Let's just have a model where we say it stops, and it gives its energy to the lattice. Dumps all its energy in the lattice, and it goes again. Or you could say it does bounce, but the average velocity after it bounces is 0, right? Because it has just as good a chance of bouncing that way as it does of bouncing that way, because all these little billiard balls are bouncing around. So you can think of it as stopping, or you can think of it as being randomized, okay? if the velocity after it hits is randomized, then the average, the typical, if we're looking at a lot of electrons, is going to drop to 0. If you thought of them as all accelerating and then they all collided, when they're accelerating, they all have a uniform velocity moving forward, and they collide and they're all random. So you could think of this as the average velocity of a bunch of electrons. Either way you want to think about it, it did accelerate for a while, and then it stopped because it hit something. Once it hits something, it's just got to pick itself back up and keep going. There's still an electric field, so it's going to accelerate again. Oh, and then it hit something, back down to 0. And it's going to accelerate again. Oh, and this time, oops, same slope. It's this time there was something too close, and it hit early. And then it's going to accelerate again. Oh, it hit something like that. So this is, in the Drude model, this is the trajectory of the electron as it flows through the metal. Is it accelerates and then it hits, crashes, accelerates, crashes, accelerates, crashes. So what you end up with is, if you were just to not take the average, is it actually floats along with sort of an average velocity that we call v drift. And if we characterize the typical time between the collisions as tau, we can figure out what v drift is. Right? So velocity equals acceleration times time. Okay, so then velocity is going to be the acceleration. What's the acceleration? It's, let's see, well, it's the F equals QE, so it's the force, the QE over m, sorry. QE over m is the acceleration, and time is tau. We're figuring out how fast does it get. That's tau. So we can write v drift that way as QE over m times tau. So this is why we imagine them having a constant drift velocity when really they're accelerating all the time. They're accelerating and stopping, accelerating and stopping.